Discrete IO Modules. The idea behind a discrete IO module is that it's made for interfacing with things that are either on or off. And so it's a bit-oriented input-output type of module, because everything that's coming in, whether it's a button, that button's on or off, and that's a 1 or a 0. Relays going out are 1s or 0s, they're on or they're off, and so forth. So there's all sorts of things, very useful devices that can be either on or off, and so discrete IO modules handle these types of signals. Now it's really important to understand that each of these modules, whether it's an input or an output, has to be powered in some way. And students get really confused about this because they think that, as soon as they put the module on the side of the PLC or drop it in the slot, well then it's like a power outlet, for example, in the output, and they can just plug devices in it and it will provide power to it. That's not the way it really works. You need a field supplied voltage source. What that means is that, yeah, the IO module may make connection or not for a particular point, but no power flows through it until you apply a power supply. So you might wonder, well, why on earth would you do something like that? Well, the reason is because you might want 24 volts DC, which is a really common control level voltage. You might need 120 volt AC to power some output. On my PLC that controls my heating system in my home, I have a 120 volt AC input signal so that I can know when a particular pump is on. I have a separate controller that's sort of a dumb controller. I can't interface it easily to my PLC, and all I really need to know is when that dumb controller turns on its pump. So all it is, I wire wide an output off of the pump motor, so that when the pump motor has 120 volts across it, so does this wire, and I connected it to 120 volt input AC on my PLC. So there's all these different voltage levels that are very useful depending on what type of device you really want to use. You might wonder, well, why don't they make all these devices just operate off of one control voltage? Well, it's for flexibility. There's many reasons not to. Having to do with distances, AC and DC act differently over distances, and anyway, so there's many reasons why you would want an input-output module to be able to support a particular output voltage or input voltage specification. So the logic in the modules receive their voltage from connection to the PLC, whether it's through a backplane or if it's a daisy-chained setup. So by default, the IO modules receive some power from the power supply used to drive the PLC, but field power has to be connected typically to the front face of these devices, and it's the field power that powers the sensors and the output devices. Now, one thing about this is you have to worry about your power budget, and what that means is as you add more and more modules, each module is going to draw a certain amount of current. And you got to keep track of how many modules you've got, IO modules, and the PLC draws some power as well, and make sure that the power supply for the overall machine, or for this overall PLC, is capable of supplying current not only for the PLC brain and memory and so forth, but also for the input-output modules. Now, understand, we're not talking about field device power. Sometimes people will wire off of this power supply and also connect it to the front of the IO modules for field power. And you can do that, you just have to be very aware of power budgeting. One nice thing in the Click software is you can go into the setup, I think it's system setup as I recall, and get an idea of how much power each module is going to draw so that you can select an appropriate power supply. Now let's delve into a little more detail of these input-output modules, and we'll look at one particular input point. So this is an input point from an AC discrete input slot or card, I guess you'd call it, module. So you can see on the left-hand side where we've got a 120 volt AC signal that we want to put into the PLC input point in order to indicate that something's on. And of course, the input signal is blocked by a switch. The switch is the sensor, right? When we press that switch, that's when we want this 120 volt AC signal to go in. So the first thing that has to happen is a bridge rectifier that rectifies the AC, and then another section that sort of processes it. And then there's a really important piece here called optical isolation. If you think about a signal at 120 volts AC, you do not want that at any time to connect to your logic circuits. The problem is that the logic circuits on the module are connected to the brain of the PLC, and if you can put 120 volts on those logic circuits, you can fry the brain of the PLC. You don't want to do that. So again, for the sake of robustness and ruggedness, all inputs on any decent PLC are optically isolated in order to prevent problems from occurring if an input, say, is overloaded with voltage or something. So there's essentially the power section, which is what converts whatever input voltage you have to what the optical isolation device needs. And then there's the logic section afterward that actually communicates to the PLC. Now the logic section, in almost every case, is connected to also a light emitting diode, an LED, that's on the face of the input or output module to indicate that that particular input point is either on or off. And these are very handy for troubleshooting because, you know, if for some reason your PLC doesn't behave the way you want it to, and you trace the problem down to potentially one sensor, how do you know if it's the sensor that's the problem or if the PLC has a problem? Well, that input status indicator, that LED, that light, can very easily turn on and off. And a lot of times what you'll do is you disconnect your sensor and just, you know, force power into that input point, and you'll see the light come on. You know the PLC is okay. Or if the light doesn't come on, then you know the PLC has a problem on that module. So it's a really handy thing to have this status light. A little more detail of what that circuit would look like with schematic symbols instead. Most of the time you'd want to fuse in line with the sensor, and so in this case it's just a push button sensor, but that push button is literally just wired to an input point on the PLC input module. And of course notice we're supplying 120 volts AC to the input point. Now notice that it doesn't make any sense to talk about voltage. You need to talk about voltage differences, right? What's the difference between the electric potential at the point versus what? Well, versus a common. And so every switch will have at least two wires going to a PLC input module. Now a lot of times that one of the wires is a common that's shared, but technically every switch needs two wires going in. So you notice then that after that there's some filters and resistors, and then the AC signal is applied across what's called a full bridge rectifier, a diode bridge. And what that does is that rectifies the alternating current into direct current, and then that goes through a threshold detector. We're not worried about that. Ultimately what happens though is the electricity turns on an LED. You can see the LED in the so-called optical isolator box, and this is all just one chip, the optical isolator, where that light emitting diode basically shines onto the base of a photosensitive transistor, and therefore then that transistor turns on and allows current to flow. If the voltage was too high, say this is designed for 120 and we put 240 volt on it on accident, you're going to blow up something from that input pin all the way up to the LED of the optical isolator, but that's it. After that, yeah, this module will have to be replaced to make that point work again, but at least that high voltage signal did not get into the digital logic and did not cause damage in the PLC itself or any other device connected to the PLC. So that's the general idea of the way that this works, and really all you're doing with any of the input modules is taking whatever signal that comes in and turning it into a light that turns on or off depending on whether or not the input signal is applied or not. Now an output module works much in the same way. Of course the idea here is that the PLC program is supposed to set or clear outputs, and so there's logic between the PLC's brain, if you will, and the output module, but there are also indicator lights here, which is very convenient because you can tell whether the PLC has turned an output on or off because there's a light that comes on the face of the output module. So there's logic circuits connected to the PLC's brain. And again, it would not be a good idea to have high voltage go back into that logic circuit. So another optical isolator is used on the output side for each and every output that separates the PLC's brain and the logic of the output module from the actual output to the physical world. And hopefully this will help you understand why you really need some source of power for output modules, because really all you've got is, in this case, if it's like it was before, is a transistor that's making connection. That's all it really is. There's light shining on the base of a transistor. That does not generate power to make a lamp come on or turn a motor. All that does is apply contact closure, or connection, if you will. It's not really contact closure when it's a transistor, but relay outputs do have contact closure. But even those require some field power, some power to the module itself for the sake of the output devices. So you can see the load here, and once the electronic switch is on from the transistor and the optical isolator, then power can flow through the load, the lamp in this case. So it's key to understand that you've got to have power for input modules and for output modules that is field power, that is totally separate from the power used to drive the logic circuits, which actually comes from devices connected to the PLC, in particular the power supply for the PLC. So here's a schematic diagram of the details of an output slice, it's called sometime, or output point, where we have a particular load labeled load down there. It's connected between L2 and the output point, and then the other side of that voltage supply, that AC voltage supply, is connected to L1. And in this case, I know it's an AC voltage because they're using Triac to switch it. Triacs look like two diodes back to back, but they are used, they're not exactly just two diodes. You see a line coming off the left side of one. These are used for switching AC signals, either making contact or not. And this is there's more to the circuit than this, but essentially you can see the digital logic circuit on the left is driven by the PLC, which drives then a light emitting diode that you don't see. This is separate from the LED indicator that you do see, because this LED in the optical isolator is inside a piece of usually black plastic. You can't see its light. I think it's infrared anyway, and you wouldn't see it. But it drives the base of, again, a photosensitive transistor. And that finishes the optical isolator, but then that allows the Triac to turn on, which makes connection so that current can flow through the load and up through the Triac and then through the fuse and then out L1. Of course, it would be AC, so it would be flowing back and forth. So in this way, the PLC, although it doesn't have 120 volts to give, it can turn 120 volts on and off. That Triac you can think of just as a switch, something that closes and opens, because electrically that's all it's really doing. Now, most AC outputs are limited by the size of the Triac. Triacs are not devices that can, drive, say, a 100 horsepower motor or something. Okay, if you have a 100 horsepower 110 motor, you're not going to drive that with an amp. There's no way. And so, a lot of times, if you have a 120 volt AC output from a Triac, it's used for a small load, or it's used to actually drive what's called an interposing relay, a relay that actually does the job of connecting power to the motor device. So you'll notice L1 and L2 are legs that, it's not shown exactly how, but you can see L1, L2, L3. That's where power is actually coming in from the power companies, L1, L2, L3. L1 and L2 are connected to the output module because you have to have field power somewhere. So there it is. And then there's an interposing relay so that the output, which is the blue terminal, turns on the interposing relay coil. It drives that, which closes switches, which then turns on the main switches, the CR switch you see there, that allows current to flow through the larger motor coil starter and then turn on the motor. So there's really two relays here, if you think about it. There's the interposing relay, which is a typically fairly small relay whose coil can be driven with an amp or so. And then there's the bigger relay that requires more current, that is actually the motor starter. And you can see the motor starter coil there. And of course, that motor starter coil then is driven by the interposing relay, because when the interposing relay's coil comes on, that pulls in the switch labeled CR, which then allows the main coil to come on and the motor to start. Now, there's several different types of devices that can be used for output slices or output points or output cards or modules. Here are the big ones. There's Triac Outputs, which we've already seen, and they're useful for switching AC. So if you got an AC source, a Triac, can turn that, it can make connection to the load so that current can flow, or it can break that connection. Relay outputs are very popular, they're very common, they're relatively inexpensive, and they can transfer a relatively high amount of current. Now, relay outputs are, you see a picture of a relay here, that's not what they look like on the inside of the PLC output module. Inside of the module, they're much smaller devices, and so the current capacity that their little switches can actually stand up under and transmit is limited to some extent. Of course, with relay outputs, the other problem is it's a literal mechanical switch. It's going to wear out over time. The other problem is it can only switch on and off so fast, so it's frequency limited, and you do not want to turn a coil or a relay output in a module on and off at even 1 hertz. That's not a very good use of it, because you'll run out of cycles. Its life will be done fairly quickly. When coil switches or the switches inside of the relay make and break contact, there's sparking that occurs, and every time there's a spark, a little bit of material is removed, or some carbon buildup occurs, or whatever the case may be, and it damages it. Now, the nice thing about relay outputs is you can switch any kind of current you want. It can be AC, it can be DC. A wide ranges of voltages is typically just fine. Whereas with a Triac, you can switch much faster, and there's no mechanical movement, but you can only switch AC with that. If you want to switch DC, then you need to use some type of a transistor in order to switch DC. Now, all of these details are taken care of by the manufacturer. But if you hear somebody say, well, this thing has Triac outputs, you know what that means is that it's made for switching AC. Whereas if they say it's relay, you know it's going to be frequency limited and life cycle limited. You can't just flip them on and off continuously and expect it to last. If it's a transistor output, or also sometimes open collector is a term you'll hear a lot, and that's a particular configuration of a transistor output. Anyway, that's used for switching DC, and you'll get used to these different terms. And of course, there could be multiple different types of Triac modules that are made for switching different levels of voltage as well, and different amounts of current. Some more expensive than others. Typically, as the current capacity goes up and the switching frequency goes up, the cost of the module goes up. Now, here's a topic that confuses students all the time. It's syncing and sourcing. As a matter of fact, I have a whole separate lecture on this that I'm going to give you. But the basic idea between syncing and sourcing is actually very, very simple. A syncing thing, no matter whether it's an input module, a sensor, an output device, it doesn't matter what it is, a syncing thing is connected to the return. It's connected to the negative of the power supply, or the neutral of an AC line. Whereas something that's sourcing is connected to positive or hot. That's all there really is to it. And so, if you've got a syncing sensor, you're going to have a sourcing input module, because for current to flow through the whole loop, you've got to have a complete circuit. And so there's going to be 2 wires that go to the input module, and one side is going to be connected to the switch, and the other side is going to be connected to the power supply. So you can see that the positive of the power supply is connected to the sourcing input module, and that's why it's sourcing. It's because it's the thing that is holding hands, if you will, with the positive side of the supply. On the other hand, the sensor is holding hands, again, if you will, with the negative side of the power supply. So it's what provides the part of the circuit loop that's connected to common. Now, students make the mistake of calling the negative side ground, and I'll make that mistake too as time goes on, I'm sure. But really, there's a difference between ground and common, although sometimes they're tied together in a DC power supply. But ground is really the electrical wire that's somewhere outside of the building. There's a rod driven into the ground, and that's why it's called ground. With the output example here, the output is a sourcing output, and the reason it's sourcing is because it has a permanent connection to the positive side of the power supply, whereas the field device, whether it's a lamp or a motor coil or whatever it may be, always has connection to the negative side of the power supply, or the return path. And so it is considered a syncing field device. Now, you can have the opposite situation too, and the important point here is that some input modules and output modules are syncing, others are sourcing, and some can do either. But beyond just whether you want to use AC or DC and what voltage level you want to use. You also have to know whether or not the device you're going to use is a syncing or sourcing device, so that you can choose the I/O module appropriately as the opposite. You would never have a sourcing module with a sourcing sensor, for example, a sourcing input module. If the input module is syncing, then the device, the sensor, is going to be sourcing. And you'll notice everything in this slide is just opposite of the last one.